Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Dr. Shahid Amin, and in this session we are going to discuss our second part of lecture 6 on biosynthesis of natural products with course code Chem 524. This lecture is also continuation of lecture 5 and 6, first part of lecture 6, that is the construction mechanism for secondary metabolites. That is actually part of the bigger topic, that was the major biological events occurring within living organisms. So let's see what we have to discuss in this session. In this session we will discuss two main topics. The first one being transamination reactions, and the second one is decarboxylation reactions. Okay, first we see what do we mean by transamination reactions. As the name shows, transamination, that is amino group, this has to be transferred from one molecule to the other. So let's see what are the transamination reactions and what happens during these reactions during the secondary or primary metabolism. The synthesis of amino acid depends upon amination of Krebs cycle intermediate, that is 2-oxoglutaric acid, that is converted to glutamic acid. And this process is a reductive amination, that is amination that is brought about by a reductive process, a reduction process. So simply we can represent this reaction like this is our 2-oxoglutaric acid. It will accept amino group from some amino donor and will be converted to glutamic acid. So this keto group will be converted to a primary amino group. So because oxygen is being removed from here, so this is a reductive process, or reduction is happening here. During this reaction, imine formation happens, like in case of previously discussed Mannich reaction. Reverse of this reaction, that is if we go from glutamic acid to oxoglutaric acid, this is also important metabolically, and it gives rise to further some other amino acids along with the regeneration of oxoglutaric acid. Glutamic acid that is produced as a result of this reaction, this can participate in the formation of other amino acids via transamination reaction, as it has been shown in this part of this figure. The exchange of amino group from one amino acid to a keto acid, this is the most common process for the introduction and removal of nitrogen into or from amino acids. So the amino group is transferred from one compound to the other because of these transamination reactions. Now we look at what's the mechanism of transamination reactions. These reactions are catalyzed by the enzymes that are known as transaminases. And in addition to these transaminases, these processes also utilize some cofactors like this coenzyme pyridoxal phosphate, or PLP. And during this mechanism of these reactions, imine intermediates, or aldimines, these are involved. So if you start from this amino acid, this is any amino acid. During the transamination reaction, what happens that here, this is our pyridoxal phosphate, and it has an aldehyde group. This aldehyde group may react with this amino group. As a result, we'll be having formation of an imine. So this is imine that has been formed. This imine will rearrange further, that is, it will lose a proton from here. Both of these electrons, they will be coming here, making a double bond here like this. And now nitrogen will be having 4 bonds, so this bond will be shifted here, and further this electronic cloud will be shifted inside this pyridine ring and ultimately towards nitrogen. So this nitrogen will accept one proton. We can see here that it will accept one proton to be converted to this NH group. So this N that was part of this aromatic system, it now, this nitrogen atom acquires this hydrogen, And here we have this type of structure formed. So we can see there is extensive conjugation in this whole molecule. Now what will happen? Further rearrangement will happen, that is the hydrogen that is here in the form of we can say a proton. This is protonated form of this species. So this hydrogen will leave from here, and this electronic cloud will be reshuffled again, and we will be having this form of this molecule. Now this is a ketimine. Ketimine. Why we have to call it as ketimine? Because this is imine. On both sides we are having carbon atoms, so this is a potential keto group, so this is a ketimine. Now this ketimine will undergo hydrolysis process just like the hydrolysis of normal imines, and it will provide us with a keto group here and NH2 here. So this pyridoxal phosphate, it has been generated, but now instead of this being called as pyridoxal because of this aldehyde, now it contains an amino group, so it will be pyridoxamine instead of pyridoxal. Al means aldehyde, and instead of aldehyde we are having an amino group, so this is pyridoxamine, and phosphate group is as such pyridoxalamine. And here we are having, instead of this amino acid, we are having a keto acid. So glutamic acid, two oxoglutaric acid couple, that is this one, it provides the usual donor acceptor molecule for the amino group, and thus glutamate transaminase is the most important of the transaminases. So this reaction could be further, I'm sorry. So this is our glutamic acid, this is keto acid, and this glutamic acid will provide this amino group to the keto acid to make that keto acid into an amino acid, and itself glutamic acid will turn into a keto acid, and the reverse process will give us glutamic acid along with keto acids. So that was the transamination reactions. Now we talk about the decarboxylation reaction. As the name shows, that this process involves a removal of carboxyl group in the form of carbon dioxide. So many pathways to natural products actually involve steps which remove part of the carbon skeleton of the secondary metabolites. Decarboxylation reaction is considered the most common degradative modification for losing one carbon atom. Though two or more carbon atoms, these may also be cleaved off via the reversal aldol or reverse Claisen reaction. It's a particular feature of the biosynthetic utilization of amino acids to produce several of the basic building blocks like these aromatic systems, C6C2N, and another aromatic system, indole C2N, that we discussed in our building block session of these lectures. Now we look at the mechanism of decarboxylation reaction. Decarboxylations of amino acids, this is also a PLP, that is pyridoxal phosphate dependent reaction, and shares features of the transamination reaction. As we can see here, that this is our amino acid. By reaction with PLP, it will be converted to this imine. So the first step will be imine formation. This imine of this carboxylic acid, it will lose this carbon dioxide because this bond is highly polar. So this electron may shift here, and this electron may shift here in order to make a double bond here. Nitrogen will have 4 bonds, so this double bond will be shifted here, this one will be shifted here, and this double bond will be shifted as electron pair to nitrogen that will be donated to proton. So this nitrogen will get protonated. So as a result, we will be having this structure, but with the loss of carbon dioxide. So in this process, in this reaction, decarboxylation, or in this part of this process, decarboxylation or removal of carbon dioxide is happening, and we are having a species like this. Now, if this species takes up one proton, it will be converted to this product, that is a Schiff's base, and this Schiff's base afterwards, because of hydrolysis, it will give us this pyridoxal phosphate along with this aliphatic amine. So amine formation will have amine will be generated from carboxyl group. So if amino group is lost, we get a keto group here, so alpha keto acids are produced. But if this carbon dioxide is removed, then we get simple amines. So this is one of the examples of decarboxylation reactions and the way this happens. Beta keto acids, they also undergo decarboxylation reaction because they are thermally labile, and rapidly they can decarboxylate even in vitro via a cyclic mechanism through the enol form of the final ketone. So similar reactions like these are happening in vitro. Similar reactions are found in nature also, although it's not known whether the cyclic process is necessary or not. So this is our beta keto acid, keto group, alpha carbon, carboxyl group, alpha carbon and beta carbon. At beta carbon there is this is oxo group is there. So this is a 6-membered intermediate. We can say this is intermediate because the hydrogen bonding, it's taking this molecule into this particular 6-member ring state. So reshuffling of the electronic cloud within this system, it will give us with decarboxylation. This electronic cloud will be shifted here, double bond will be generated, and this single bond will be broken. So oxygen, double bond carbon, double bond oxygen, this will be carbon dioxide, that will be lost. And ultimately, what we'll get, this electronic cloud, when this is shifted here, a double bond will be generated here. And this oxygen, after getting this proton, it will be converted to OH group. So here we are having this enol, and this is an intermediate in this process. Now the tautomerization of this enol will give us this ketonic compound. So beta keto acids, these are converted to their respective ketones by losing carbon dioxide. Similarly, orthophenolic acids, these also decarboxylate in vitro and in vivo also. And it's again possible to invoke a cyclic beta keto acid tautomer on the substrate, as we have seen before. So here, this we can regard this phenolic compound as an enol. So this enol, it will undergo tautomerization, and once it gets tautomerized and it goes into the keto form, then again similar cyclic ring is formed. A cyclic intermediate-like structure is formed, where reshuffling of the electronic cloud, it will ultimate and breaking and making of some bonds, it will give us a phenol along with carbon dioxide. So this molecule will go into the decarboxylation process. Similarly, if we have instead of orthophenolic acid, if we have paraphenolic acid, it will also undergo similar process to produce alcohol, carbon dioxide, and phenol. Now, alpha keto acids, they also undergo their decarboxylation is a feature of primary metabolism. For example, pyruvic acid is converted to acetaldehyde in process of glycolysis, and pyruvic acid, when it leaves glycolysis and has to enter Krebs cycle, it has to be converted to acetyl coenzyme A. These are examples of overall, that is an example of overall oxidative decarboxylation. They could be explained in a way that in both of these reactions, one thing that is involved and the reactions depend upon, this is thiamine diphosphate. This coenzyme contains a thiazole ring in the form of thiazolium salt. So the process, it will, if we talk about pyruvic acid to acetaldehyde, the process of glycolysis, it will happen like this is the structure of TPP. It has this hydrogen that is acidic hydrogen because of presence of this positive charge upon this nitrogen that makes this this carbon partial positive, and because this hydrogen attached to this carbon, so it also because of inductive effect gets partial positive charge. So this is acidic hydrogen. A basic species may take up this proton, and as a result the electronic cloud reshuffles, and this electronic cloud, it's concentrated upon this carbon. So when there is a negative charge upon this carbon, there is a positive charge on this nitrogen that is attached to this carbon. So this is a ylide-like species. So this is TPP ylide. So this ylide is highly unstable. So when pyruvic acid is in close contact with this ylide, its negative center will attack this partial positive carbon of this keto group, and these electrons will flow towards oxygen, where they will take up one proton from the medium to be converted to an alcoholic group. So ultimately, as a result of this process, we will be having enol type of structure, like this is a double bond, and then here we are having alcoholic group. So here, this molecule rapidly undergoes decarboxylation because of rearrangement of the electronic cloud and breaking and making of some new bonds. As a result, we have this enamine. Sorry. So this enamine, it will get protonated because this nitrogen that has got a lone pair of electron because of the shuffling of this electronic cloud. Now this lone pair will be donated here, and this double bond, it will its electronic cloud, that is pi electronic cloud, it will flow towards this proton, and we will get again this enol type structure that because of reverse aldol type reaction, it will give us our aldehyde along with the original ylide that was produced because of the action of base upon this TPP. So this way, acetaldehyde is produced as a result of decarboxylation reaction. If we talk about the production of acetyl coenzyme A from pyruvic acid, that is just another reaction of decarboxylation, but it's oxidative decarboxylation. The enzyme-bound disulfide containing coenzyme lipoic acid, this is also involved in addition to TPP that we discussed in the previous slide. Now, the intermediate enamine, instead of accepting a proton, now is used to attack a sulfur in lipoic acid moiety with subsequent sulfur-sulfur bond fission, thereby effectively reducing the lipoic acid fragment. It could be shown simply as this is our enamine that is we have discussed in the previous slide. So if it has to go towards formation of acetaldehyde, then it will take up one proton. But if instead of taking up one proton, it attacks the sulfur of lipoic acid moiety, then it will go towards the formation of acetyl coenzyme A in an oxidative process. So when this pi electronic cloud attacks this sulfur, we have a species like this, and this species after rearrangement and breaking of this bond, it will produce the ylide, and along with this acetylated lipoic acid moiety that will actually react with coenzyme A, and this acetyl group will be attached to coenzyme A to be converted to acetyl coenzyme A, and we'll get this reduced form of lipoic acid. This reduced form of lipoic acid will get oxidized when it reacts with FAD, that is an oxidation reaction itself being reduced to FADH2, and this lipoic acid will be generated.